In a properly functioning electrical system, the neutral return voltage should ideally be 0 volts. This is because the neutral conductor is intended to provide a return path for current that is equal and opposite to the current flowing through the hot conductors. To understand this, let's delve into the fundamentals of a typical American electrical panel. The panel you described, a 400 amp, 120 volt, 60 Hz two-phase system, is a common configuration. However, it's important to note a standard American residential service is typically single-phase, not two-phase. Two-phase systems are less common in residential settings. Assuming it's a single-phase, three-wire system, which provides both 120 volts and 240 volts, it operates with two hot conductors, a neutral conductor, and a ground conductor. The 120 volts is derived by taking one of the hot conductors and the neutral. The 240 volts is derived by taking both hot conductors. The neutral conductor's primary function is to carry the unbalanced current back to the source, which is the utility transformer. In a perfectly balanced system, where the load on each of the hot conductors is identical, the neutral conductor would carry no current, and consequently, there would be no voltage drop along the neutral conductor. Therefore, the voltage between the neutral and the ground should be 0 volts at the panel. However, in reality, perfect balance is rarely achieved. There will always be some degree of imbalance due to varying loads on different circuits. This imbalance results in current flow on the neutral conductor, and because the neutral conductor has some impedance, a small voltage drop will occur. This voltage drop is what we refer to as neutral return voltage. The amount of neutral return voltage considered acceptable depends on various factors, including the size of the service, the length of the neutral conductor, and the amount of unbalanced load. However, a general guideline is that the neutral return voltage should be kept as low as possible. A voltage of more than a few volts could indicate a problem. Several factors can contribute to excessive neutral return voltage. Firstly, loose connections in the neutral conductor can significantly increase impedance, leading to a higher voltage drop. Secondly, an overloaded neutral conductor can also cause excessive voltage drop. Thirdly, improper grounding or bonding can create alternative paths for current flow, resulting in voltage on the neutral conductor. It's crucial to understand the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth, providing a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and clearing the fault. Bonding refers to connecting all metallic parts of the electrical system together, such as metal conduits, enclosures, and equipment frames, to create an equipotential plane. This ensures that all metallic parts are at the same voltage potential, minimizing the risk of electric shock. The neutral conductor is bonded to the ground at the service entrance. This is the only point where the neutral and ground should be connected. Connecting the neutral and ground at multiple points can create ground loops, which can lead to unwanted current flow on the ground conductor and potentially increase neutral return voltage. Now let's discuss how to measure neutral return voltage. Firstly, you will need a digital multimeter. Secondly, set the multimeter to alternating current volts or alternating current millivolts. Thirdly, place one lead on the neutral busbar in the panel. Fourthly, place the other lead in the ground busbar in the panel. The reading on the multimeter will indicate the neutral return voltage. If you measure a significant neutral return voltage, it's essential to investigate the cause. Firstly, check all neutral connections for tightness. Secondly, verify that the load is balanced as much as possible. Thirdly, inspect the grounding and bonding system for any issues. If you are not comfortable working with electricity, it's best to consult a qualified electrician. Remember, working with electricity can be dangerous, and it's essential to take all necessary precautions to avoid electric shock. Here are some additional points to consider. The National Electrical Code, NEC, provides detailed requirements for grounding and bonding. It's essential to follow the NEC guidelines to ensure a safe and properly functioning electrical system. NEC Section 250 covers grounding and bonding requirements. Equipment grounding conductors X are used to connect metallic parts of equipment to the grounding system. These conductors provide a low impedance path for fault current. Ground fault circuit interrupters, GFCIs, are designed to protect against electric shock. They detect small imbalances in current between the hot and neutral conductors and trip the circuit if an imbalance is detected. Arc fault circuit interrupters, AFCIs, are designed to protect against fires caused by arc faults. They detect abnormal electrical arcs and trip the circuit. Regular electrical inspections are recommended to ensure that the electrical system is in good condition. An electrician can identify potential problems and make necessary repairs. In summary, the neutral return voltage in a properly functioning electrical system should ideally be 0 volts. A small voltage is acceptable due to imbalanced loads. Excessive neutral return voltage can indicate a problem with the wiring, grounding, or bonding. It's essential to investigate and correct any issues to ensure a safe and reliable electrical system. Always consult a qualified electrician if you are not comfortable working with electricity. For a 400 amp service, the neutral conductor size is determined by NEC table 310.15. B16, but it must be sized to carry the maximum unbalanced load as per NEC section 220.61. The grounding electric conductor size is based on the size of the service entrance conductor, as specified in NEC table 250.66. Bonding jumpers are used to connect metallic parts of the electrical system together. The size of the bonding jumper is based on the size of the largest ungrounded conductor, as specified in NEC table 250.102. Seat 1. Surge protective devices, SPDs, can protect against voltage surges caused by lightning or other events. They should be installed at the service entrance and at sensitive equipment. Understanding the principles of grounding, bonding, and neutral return voltage is crucial for ensuring a safe and reliable electrical system.